In the previous video, we have seen that chlorides can lead to localized steel corrosion in concrete. The problem is that steel sectional loss is not visible, as it can take time before cracks and rust stains appear at the concrete surface. Measuring the potential is a suitable technique to detect localized corrosion in concrete non-destructively.
As seen in the previous video, chloride-induced corrosion leads to macrocell corrosion. The flow of the macrocell current leads to potential differences at the concrete surface. These potential differences, together with a number of other effects, allow detecting localized corrosion spots in concrete structures. Different national standards give guidance on how to measure and interpret potential measurements. For instance, the Swiss SIA Merkblatt 2006. To measure potentials of steel in concrete, we need a reference electrode in contact with the concrete, an electrical connection to the reinforcing steel, and a voltmeter. The reference electrode generally consists of a copper rod in a solution of saturated copper sulfate. As we have seen in video 1, the copper metal in a saturated solution of copper ions delivers a stable reference potential. The electrolytic contact to concrete is ensured with a diaphragm, such as a wooden plug and a sponge. By moving the reference electrode along the structure from point to point, potentials can be measured at different locations. In general, the more negative the potential, the higher the probability for corrosion. In practice, hundreds to thousands of potential measurements are done, usually on a regular grid with spacing between 15 to 50 centimetres. For this purpose, a reference electrode in the shape of a wheel is more convenient and more efficient. Wheel electrodes are more complex than the single-point electrodes seen before, but they contain the same essential components. A copper part in a container with copper sulfate solution and wooden plugs to ensure contact to the concrete. Here we can see how such wheel electrodes are used on an engineering structure, for instance on walls or overhead structural members up to a limited height. For even more efficient measurements on a top surface, arrays of 4 or even more electrodes are also used. The measurement results can be directly viewed on the screen of the measuring device on the construction site. The result of potential measurements is often shown as a colour plot to highlight the spatial distribution of the measured potentials across the structure. It is important to recognise that a generally applicable threshold potential indicating corrosion does not exist. As seen in the previous video, the potential depends on several factors such as the oxygen concentration or the pH. Thus, the analysis and interpretation of potential mapping is more complex than just applying a simple threshold value. Here we show a statistical procedure to analyse the data. First, the measured potentials are plotted as a histogram. We assume that 2 Gaussian distributions are present in the histogram, one for the potentials of the actively corroding steels and one for the potentials of the passive steel. By mathematically fitting 2 Gaussian distributions to the potentials, we have a sound and operator-independent basis to further interpret the measurements. In this example, we find that below -240 mV versus the saturated copper sulfate electrode, virtually all potentials belong to the active distribution. Above -170 mV versus the saturated copper sulfate electrode, on the other hand, virtually all potentials belong to the passive distribution. For the range between these potentials, it is difficult to make a statement. Now we can redraw the colour plot with the 3 corrosion risk classifications according to the statistical analysis. To validate the interpretation of the corrosion state in the different regions, additional sampling and destructive testing are needed. First, the measured potentials should be compared with visual observations such as cracks or spalled areas on the concrete surface. Furthermore, it is important to remove the concrete cover in selected areas in order to visually inspect the steel. Additional information can be obtained from carbonation depth measurements and chloride profiles, which generally requires core drilling and additional laboratory testing. Further non-destructive methods such as cover depth and electrical resistivity measurements may add valuable information. In this video, we have seen how localized corrosion spots can be detected non-destructively with potential measurements at the concrete surface. The correct interpretation of potential measurements requires validation at selected spots through additional testing and specialized expertise. The main advantages of potential mapping are that this technique allows assessing the full surface of a structural member, and that it can reveal zones where active corrosion is ongoing, but where this is not yet visibly apparent. Thus, potential mapping is a powerful inspection method to support the planning of maintenance and repair.
In these 4 videos, you have learned the corrosion fundamentals, corrosion of steel in concrete, and how to detect localized corrosion in concrete structures. These are important aspects in civil engineering, in particular concerning the durability of reinforced concrete structures.